Good day everyone. So today I will make a short tutorial dealing with motion graphs with multiple cases of motion. So these are compound motion graphs. That's not just one line going this way and one line going that way. It's multiple lines that go up and down and left and right, etc. But in order to deal with this, I have come up with a five-step plan in order to do this. Now I added this step 3 because right now we are actually going to calculate. Before we were just making rough sketches of what the graph would look like, but now we are going to try to integrate some numbers. So split the graph, analyze the case of motion in each, calculate for the exact values of total displacement and etc. Draw the graph and reconnect the segments. Okay? And actually, I'm going to also have a quick review. So the slope of the line of a position time graph is its velocity because the slope of the line is y over x. Okay? And again, the slope, the y-axis of a PT graph would be p, which is meters. And the x-axis would be time, which is seconds, so that's velocity. As for the VT graph, this one would become meters per second. So when this simplifies, this simply becomes meters per second squared, or is the acceleration of the graph. Okay, now for area under the curve, PT graph, you can't really get an area under the curve because that's meters times second. But for VT graph, because most of the areas, let's say you're getting the area of a rectangle, that's simply base times height. And for a VT graph, the base of your graph would always be time. So that's seconds. But the V, or the y-axis, or the height, is meters per second, which is velocity. Cancels out, becomes meters. This is a displacement. Now, this is something I also didn't introduce in class, but for an acceleration time graph, meanwhile, so if it's base times height, same, your x-axis will be seconds, but this time acceleration has a unit of meter per second squared. So if you were to get the area under the curve of an acceleration time graph, this would cancel out. You'll be left with meters per second. You're actually getting your velocity. Okay? So that is just a review of motion graphs. Now let's tackle a sample problem. Okay, so I'm here given a velocity time graph. And take note, if I go back to my notes again, the VT graph is literally where you could get almost all the details. So most of the time when we're dealing with problems like this, we're starting with a VT graph because you could get acceleration and displacement straight off the bat. But anyway, let's have a problem like this, wherein we have a velocity time graph, goes down, goes sideways up, and then perfectly horizontal again. So what's the first step? The first step is to split the graph into certain segments, okay? So it's conveniently, as you can see, divided by 4 seconds. 1, 2, 3, 4, 1, 2, 3, 4, etc. until we get to the beyond the 30-second mark. So let's try that. So I'll just put the paper this way. And there are 3 graphs here from position time to acceleration time. So I'm just going to draw a line that divides all of them by segments, okay? And take note, I'm dividing it here because this one is a different case of motion to this one. This is positive and this is negative. So let's try it. Get this. Let me divide quickly. Oh, that didn't really do much. My apologies. Okay, better. Let's divide this. And this. Let me move up my camera. Okay, divide this one. Divide this. And this. And we can leave this the last bit as a segment on its own, okay, because it doesn't really change cases of motion. So we have quite a lot of segments to deal with here. Let me just label them quickly. Segments A, B, C, D, E, F, and G. Wow, so that's 7 segments. Okay, so first things first, we've now divided them into segments. The idea now would be to analyze each segment for what they are, given the velocity time graph. So let's start with segment A. So segment A depicts that your velocity starts off at 4 meters per second, positive 4 that is, and it goes down to 0 at the end of segment A. So when you're going from 4 meters positive to 0, and in the positive direction, that is, you start out with a positive velocity, you end at 0, you're actually slowing down, okay? You're approaching 0. Approaching 0 means slowing down. So segment A would be positive direction, slow down, okay? Now let's go into segment B. It's still the same line, meaning it's the same slope. However, this time we're now in the negative direction. And this time, when we were approaching 0 earlier, we're now actually moving away from 0. So if your number is moving away from 0, so 0, -1, -2, -3 meters per second, you're actually going faster, okay? You're going faster, and that means, but you're going faster in the negative direction. So that means you are actually negative, but going faster, accelerating. Segment C. So this time, you're at -4 meters per second. You're maintaining a speed of that. It doesn't really change after a while. So this means that you are in a constant speed. Negative, but constant speed. Segment D, meanwhile, sees that you go from -4 to 0. Now, I know it's going up. However, take note again. You are going from a deeply negative value into 0. And when that happens, you are actually slowing down. So -4, -3, -2, -1, and 0. Okay? Slowing down but in the opposite direction. But you're still below 0, so you are in the negative direction, but slowing down. Okay? Now let's look at E. As you could see, it's a straight line, so your velocity doesn't change. But crucially, it's a straight line at 0. So that means that you are at rest for segment E. You're not moving. Now let's look at segment F. So in segment F, as you could see, you go from 0 to 4 meters per second. You could draw a straight line going to 4. It's 4 meters per second. Excuse me. And because you go from 0 to 4 in the positive direction, it can be said that you are speeding up because you're going from 1 meter per second, 2 meters per second, and so on. So, speeding up. Actually, just to be consistent, I'll just call it fast. Okay, so you're speeding up in the positive direction. And now for segment G, which is the longest segment of the lot. So you go for 6 seconds, going to 30, okay? And you go at 4 meters per second to 4 meters per second. So you don't change your velocity, you don't change your speed. So you're still going in the positive direction, but it's now at a constant rate. Okay, so this is actually interesting, this graph, because I think it pretty much has every single case of motion that we could actually hope for. Okay, so because of this, we can make a graph that depicts all of these cases of motion in both the displacement and the acceleration time. So after we've analyzed each one in turn, we can now go to the next step, which I didn't really introduce much in class, and that is to calculate the certain parameters. So from a velocity time graph, if you may recall, let's get the position time first. So in order to get the exact values of the position, we can actually get the area under the curve, because the area of the velocity time graph is simply your displacement, as you can see here, meters. Okay, so what are the areas under the curve? Well, in order to get the area under the curve, we must get the distance from 0. Okay, so in this case, this is 0. So the area under the curve would be this triangle over here. Take note, I'm not going all the way down, I'm stopping at 0. Okay, for this bit here, segment B, it's actually this area here. Why not this one? Because again, it's the distance from 0 that we're after. Okay, it's the distance from 0. It's not the one below 0 actually. It could be just the distance from 0, the x-axis. So this is the area under the curve. I know it looks weird because it's above the curve, but still, area under the curve, this. For this one, because again it's negative, we just simply continue this line. And actually it goes all the way to segment D. This is the area under the curve of segment D. Okay? For E, well, we're at 0, therefore there's no area under the curve. It's simply like that. For segment F, meanwhile, the area under the curve of segment F would be the distance going from F to the x-axis, which is a 0, so it's this bit. And we can simply continue that because G is also completely positive. So why is it that in some cases it's the area above the curve, like here, and some cases it's the area under the curve? You have to remember, you are getting the position, you're getting the displacement in this case. And if you're getting the displacement, you have to take note that there's a positive displacement, meaning you're at the positive position, and there's also a negative displacement. So these areas over here represent the fact that you are adding to a positive displacement, and these areas over here represent the fact that you are subtracting from that positive displacement. You're going in the negative direction of motion. Okay, so now that we've done this, we can do a bit of calculations to get the specific areas under the curve. Okay, so I'll get my calculator over here and try to figure this out. So the first bit, segment A. In segment A, as you could see, it's a triangle. So the area of a triangle, again, if you would recall, 1/2 base times height. Okay, and 1/2 base times height means that the base is 1, 2, 3, 4 seconds, and the height of your triangle is also 4 meters per second. Okay, that cancels out. You can actually do this manually. So 4 times 4 is equal to 16 divided by 2. So this is an area of 8 meters. I know it's an area, but again, we're basing it off the units of this one. We're not computing for the area of a specific triangle like this. We're computing for things that interpret in the graph. Okay, so 8 meters of displacement in the positive direction because it's above 0. Now for the bottom bit, okay, same thing, 1, 2, 3, 4. 1, 2, 3, 4 meters per second. It's actually the same triangle but in the negative, so we can just say that this is also negative 8 meters. Okay, they cancel out. Now this bit here is a rectangle. Now the rectangle has an area that is given by base times height. Okay, so that's 1, 2, 3, 4 seconds across and also 4 seconds deep. Therefore, 4 times 4 is simply 16. Okay, but because we're in the negative, this is negative 16 meters. Okay, next, this one. So in this bit here, it's actually very similar to this triangle here. 1, 2, 3, 4 seconds across and 4 seconds deep. So we can say that this is negative 8 meters. Okay, because we're still in the negative. For this one, there's no area because it's at 0. So we can just say that this has a displacement of 0, which makes sense because this one is a case of motion of rest. Now this one, okay, for this segment F, it is 1, 2, 3, 4 seconds in base, and the height is actually level to this. Sorry, I'm trying to align my pen. There we go. Okay, 4 meters high. So that's actually very similar to this triangle over here in that it is at the positive 8 meter displacement. Okay, and now finally this bit here. So I think it's better if we cap this off somewhere. So I'm going to cap it off at 30 seconds just so that it doesn't go overboard. I'll just cap it off here just so it has an end point. Okay, and this time it's not 4 meters across but 6 meters or 6 seconds. 1, 2, 3, 4, 5, 6 seconds is the base. The height is still 4 meters, and therefore base times height, 4 times 6 gives me 24 meters. Okay, so this one has a positive 24 meter displacement. Okay, I hope this is clear because we're now going to go into our next step, which is to draw the graph. And now we actually have values by which we can plot our points. Okay, so let's get trying. Let's test it out. So 8 meters. So again, you are slowing down in velocity. So this means that your position time graph would start out really steep and then plateau at the end. Now, what do we do with this 8 meters? You may ask, well, this is actually the point that we will plot on your position time graph. Okay, so I see here that the position time graph is divided by 1, 2, 3, 4, 5, which with each representing 5 meters. So roughly, if we want an 8-meter graph, it should be somewhere around here. Okay, because that's that one is in between 7.5 and 10 meters. Okay, so again, we have determined that this is slowing down in the positive direction. Therefore, the motion graph would look a bit like this. So starting from 0 always, you go like that. Okay, now let's take a look. 8 meters going down. So basically, that just cancels out with this. Okay, and we know that this is going in the negative and faster. Okay, so it becomes steeper and steeper going down. So it's also a continuation of this downward curve, except that it's like a parabola. So from here, we go down back to where we started at 0. And there we go, we've completed the parabola. Okay, so it just cancels out with this case of motion. Now let's go into this. 16 meters, but in a constant negative speed. Okay, so this time, we now have to plot 16 meters into our graph. So if we were to go, this is 15. So 16 should be roughly around this point. This point. Okay, let's say that's 16 meters. And because we are going in the negative direction, but in a constant velocity, it's no longer a curve. Okay, this time we're going in a relatively straight line. So let's just draw a straight line going that way at 16. Okay, I hope you're still getting this so far, that now that we're integrating numbers into the equation. Okay, how about 8 meters? But this time you are slowing down. Okay, you are slowing down in the negative direction. Okay, so the idea here would be to add 8 meters to the 16. Now, what is 16 plus 8? So that would be around 24. So there's a 25 over here. It's just about before the 25. And because you're slowing down, we're expecting the graph to become less steep as you go on. So you start off really steep and then you plateau and you become almost flat. Okay, so that's your case T. You just added 8 meters into it and you slowed down. Now let's go into E. Okay, this time you're at rest, and if you're at rest, you're not actually moving. And if that's the case, you just proceed and continue the line and make it completely flat. Rest. This case F, you are in the positive direction now, and you're going faster and faster and faster. Okay, so if you're going in the positive direction, you're now expecting this to curve up because this is position time. And if your velocity is positive, then you could see that you have a positive slope in your position time graph. Okay, so how would this look like if we were to put it in? Well, positive, constant speed, and because it's 8 meters, we have to add 8. So it's at negative 24 right now. So if you add 8, we're going to 16. So it's roughly at the same level as this. Let me just plot that. Okay, so it's roughly at here. And because we're going faster and faster and faster, it becomes steeper and steeper and steeper as you progress. Okay, so that is the segment F. And finally, for segment G, okay, what are we going to do? Positive and constant speed, and we add 24, so it's at 16 already. Negative 16, that is. And if we add 24 to that, we should end up at positive 8. Okay, so we look for 8. Okay, we look for 8. It's around here. So if this is 8, and because it's going at a constant speed, it's not going to be curved. It should go perfectly straight. So I just draw a line going there, and there we go. And that is the position time graph of this velocity time graph. It's a long drawn out process, but actually this is perfect because every case of motion has been analyzed. We've used everything up. So there's a lot of practice in this problem. Okay, so now that we've done the position time graph, let's try doing the acceleration time graph. So I've got the acceleration time graph down here. Okay, now the acceleration time graph looks a bit funny because it's just basically straight lines going here, 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 depicting the acceleration. Okay, so here you are at the positive direction, but you're getting slow. Okay, and as you could see, there is a negative slope. Now, in order to get the acceleration value, you simply have to get the value of your slopes. Okay, so what's the slope of this one? Well, what's the rise? To get the slope, it's rise over run, y over x, change of y over change of x. Here you go down -4 and you go run 4 meters. So -4 over 4 would simply give me a slope of -1 meters per second. And because this is collinear to this also has a slope of -1 meters per second. That's the slope of this line. Okay, any horizontal line would have a slope of 0 meters per second because your velocity doesn't, your acceleration, sorry, doesn't really change. Actually, I should change this. Second squared, my bad. Kasi this is meters per second. This is seconds, so dapat -1 meters per second squared. So -1 meter per second squared, 0 meters per second squared. Over here, what's your rise? You go up 4. What's your run? You go run 4. Okay, so 4 divided by 4 is simply 1. So this part here has an acceleration of positive 1 meter per second squared. Again, horizontal lines, 0. And for this one, it's almost similar to this. You go up 4, you run 4. So 4 divided by 4 is simply 1. So this one has a slope of 1 meter per second squared in the positive direction. And again, this is a horizontal line, so 0 meters per second squared. So now we have the values for acceleration, and it's time to just simply plot them in our acceleration time graph. This is actually pretty simple because acceleration doesn't change, okay? It's constant all throughout. It's uniform. We're not going to discuss cases of non-uniform acceleration. But let's see. So we know here that this is +1. We know here that this is -1, and that's pretty much all of the acceleration values that we've garnered. So in the first bit, we have a -1 acceleration in segments A and B. Okay, so I apologize. There appears to be a phone call that is being entertained in my house at the moment. So -1, sorry, should be down here. Okay, and then goes that way. Okay, -1. Then there's the bit that goes at 0. So for the bit that goes at 0, we just simply go this way. It's weird, but your acceleration actually just jumps. Okay, now let's go to +1. It says here +1. Let's go to +1, and we go this way. Okay, and finally 0. I just have to rush because I think they're calling me. Okay, +1. So again, we go this way. And finally, 0 meters per second squared. And for segment G, we just finish off like this. Okay, so the acceleration time graph looks a bit like this. It's a little bit weird, and it's a little bit choppy, but it actually represents the values of the acceleration because your acceleration doesn't change. Okay, so I hope this video enlightened you a little bit on how to do motion graphs with multiple cases of motion. Thank you for watching, and I wish you luck in our tests to come. Take care.